Good day, sir. I am Haider Saga from BSc 2B, and I will now discuss my answer to lesson 5, the ideal gas process. So, problem 4.2.2. There are 1.36 kg of air at 137.9 kilopascals steered with the internal paddles in an insulated rigid container, whose volume is 0.142 cubic meter. Until the pressure becomes 689.5 kilopascals, determine A. the work input, B. the PV, C. the efficiency, and D. the transferred heat or the Q. So given, we have the pressure 1, which is equal to 137.9 kilopascals, the V1, which is equal to 0.142 cubic meter, and V2, which is equal to V1. So for finding the work input, we have Q, or the transferred heat, is equal to delta U plus the W. So then if the Q is equal to 0, then delta U, or the change in the internal energy, is equal to the negative of the work. So by the ideal gas, PV1 times V1 is equal to mRT, or PV2 P2V2 is equal to mRT sub 2. And if we're going to transform this equation, we have for the temperature 1 is equal to P1V1 divided by mR, and T2 is equal to P2V2 divided by mR. So we're going to use this formula in order to find the work. Now we have delta U is equal to m, or the mass, times the specific heat times the change in temperature, or the delta T. Then since we already have the equations, just have to substitute the value. So since the value of T, we just have to substitute the value of T2 and T1 to this formula, these values into this formula. So we have now the new equation. Delta U is equal to mass times the specific heat times P2V2 minus P1V1 divided by the mass times the specific gas constant. Now delta U is equal to, so simplifying the equation, so m could be cancelled, or the mass could be cancelled, and the remaining would be the CV, or the specific heat, divided by the specific gas constant multiplied by the P2V2 minus the P1V sub 1. Now for the air, the specific heat of the air is equal to 0.7186 kilojoules over kilogram. I think this is degree Kelvin. Degree Kelvin. I forgot to put degree here. And R of air is equal to 0.28708 kilojoules per kilogram degree Kelvin. Now substituting the given to the equation, we have obtain the following equation. Now performing the operations, delta U is therefore equal to 196.06 kilojoules. And since it is stated previously that if that delta U is equals to the negative work, then W is equal to negative 196.06 kilojoules. But since the work is done on the system, then the work input is equal to 196.06 kilojoules. Next is for the delta PV. So for delta PV, you have the formula delta PV, or the delta P, P2 minus P1 times the volume. Just have to substitute all the given to the formula. So delta PV therefore is equal to 78.3 kilojoules. Now for the delta EF, or the efficiency, have the formula is equal to the integral of P dV. So since V is constant, then the derivative of V is equal to 0. Thus, if this one is equal to 0, then delta F would be equal, or the efficiency would also be equal to 0. Next, for delta Q, or for Q rather, or the transferred heat, the formula for Q is equal to mass times the specific heat times delta T. So have this here, this formula in the table. But since from the given delta T is equal to 0, this is 0, then Q is equal to 0. Now this is the P diagram for this problem, and this is the T diagram. So we have here the constant volume. That's why we have the straight line here, and here is the change in temperature, wherein there is a increase in temperature. So this problem involves so from this problem, work is done on the substance since W is greater than 0, and since the delta U is positive here, then there is an increase in internal energy. Next is problem 424. A reversible non-flow constant volume process decreased the internal energy by 316.5 kilojoules. For 2.268 kg of gas, for which the R is equal to 430 joules per kilogram degree Kelvin, and the constant is equal to 1.35. For the process, determine the A work, B the heat, and C the change of entropy if the initial temperature of is 204.4 degrees Celsius. So, since it is stated here that there is a decrease in the internal energy, then delta U would be negative. The mass is equal to 2.268 kg. The R, or the specific gas constant, is equal to 430 joules per kilogram degree Kelvin. The constant, which is equal to 1.35. Now to find for the work, forgot. T1 is equal to 204.4 degrees Celsius. So in order to convert this into degree Kelvin, I just have to add 273. Then T1 is equal to 477.4 degree Kelvin. Now for the CV, or the specific heat, since it is not stated here what kind of gas was used, we have to manually calculate for the specific heat. So the formula for the specific heat is R, or the specific gas constant, divided by the constant minus 1. So substituting all the given to the equation, specific heat therefore is equal to 1.23 kilojoules divided by kilogram degree Kelvin. Now for letter A, work is equal to 0. So this is based on this, also based on this table, since work is equal to delta, or the integral PdV. So since the volume is constant, then the work is equal to 0. Next, for the delta Q, is equal to delta U. Since delta U is equal to negative 316.5 kilojoules, then Q is equal to negative 316.5 kilojoules. So as seen here, delta U and Q has the same formula. Now for the delta S, or the entropy, we're going to use the formula delta U equal to mCV times delta T. Now to solve for the T2 first, since we don't know yet the T2 is transforming this formula. T2 is now equal to delta U plus mass times specific heat times T1 divided by mass times the specific heat. So substituting all the given to the formula, we have now the value of T2, which is equal to 363.94 degree Kelvin, or 20.8 degrees Celsius. Now proceeding to calculating for the delta S, or the entropy, we have the formula for delta S, which is equal to mCV natural logarithm of T2 over T1. So it is this one for the constant volume. Now substituting all the given to the formula, have delta S is therefore equal to negative 0.757 kilojoules per degree Kelvin, since this kilogram will be cancelled, and I don't put here the degree Kelvin because it will already be cancelled. And this is now the graph for the, so this now the TS plane. So as you can observe, so from T1, or the temperature, there is a decrease in temperature. So from T1 here, there is a decrease in temperature to the T2. Next is 428. There are 1.36 kilogram of gas, for which R is equal to 377 joules per kilogram degree Kelvin, and K is equal to 1.25. That undergoing non-flow constant volume process from P sub 1 equal to 551.6 kilopascals, and T sub 1, which is equal to 60 degrees Celsius, to P sub 2, which is equal to 1655 kilopascals. So during the process, the gas is internally stirred, and there are also added 105.5 kilojoules of heat. Determine A, the T2, or the T2, B, the work input, C, the Q, or the transferred heat, the D, the delta U, or the change in the internal energy, and E, the delta S, or the entropy. So we have the following given. So for the T1, just have to convert this into degree Kelvin, just add 273. And the T1 therefore is equal to 333 degree Kelvin. Now for the CV, since it is not stated here again what type of gas was used, then we have to manually calculate it. So the formula for the CV, or the specific heat, is equal to R for the specific gas constant divided by the constant minus 1. So substituting all the given to the equation is equal to 1.508 kilojoules per kilogram degree Kelvin. For the CV, the formula is constant times the specific gas constant over constant minus 1. So substituting all the given to the formula, we now have the value of the CP equal to 1.88 kilojoule per kilogram degree Kelvin. Now for the T2, we're going to use the formula degree delta U, which is the change in the internal energy equal to the mass times the specific heat times the change in temperature. So, and then we're also going to use the formula of delta H, or the enthalpy. The formula for the enthalpy, which is equal to delta U plus delta PV equal to mCp delta T. Now, since delta U is equal to mCv delta T, we're going to substitute this value of delta U to this delta U. Therefore, for M, or since we're going to substitute the delta U here, mCv delta T plus delta PV equal to mCp delta T. Now for the V, we're going to use the formula of PV, or the Avogadro's law. PV1 is equal to MRT1. Then we're going to transform this formula to find for the V1 or the V. So V1 is equal to MRT1 divided by T1. And now, substituting all the given to the equation, we now have the value of V1, which is equal to 0.3095 cubic meter. Now for delta PV, we already have this one is the value of P sub 2 minus the P sub 1, and this is the value of the previously calculated volume. So performing the operation, the delta PV therefore is equal to 341.5 kilojoules. Now for the mass, mCv delta T, we're just going to substitute all the given to the equation. So it is now therefore equal to 2.05088 kilojoules delta Kelvin times delta T, since delta T is still unknown. Now for the mCp delta T, just again substituting all the given to the equation, now have 2.5636 kilojoules per degree Kelvin delta T. And since we already have all the needed data, we could then substitute all of this into the equation that we previously to the previous equation, this one. So substituting all the given to the equation, delta T now is therefore equal to 666 degree Kelvin. And to find the T2 here, so since delta T is equal to T2 minus T1, then transforming this equation to find the T2, then T2 is equal to delta T plus T1. Now T1 is equal to 333 degree Kelvin. So plus the delta T, which is equal to 666 degree Kelvin. T2 now therefore is equal to 999 degree Kelvin. Now for the work input, we have the formula delta U equal to mCV delta T. Substituting all the given to the equation, so the delta U is equal to 1365.886 kilojoules. Now, in order to find for the work or the non-flow work of the problem, so the formula is Q is equal to delta U plus the work. So we're going to transform this formula in order to find work. Then now the equation is WNF, or the non-flow work, is equal to Q minus delta U. Now substituting all the given to this equation, the work input therefore is equal to negative 1260.4 kilojoules. Now for the C, or the Q, it is equal to 105.5 kilojoules, so it is already given from the problem. And for delta U, since we already solved this one here, delta U is equal to 1365.886 kilojoules. And lastly, for the entropy, we have the formula of delta S is equal to mCV natural logarithm of T2 minus over T sub 1. Now, substituting all the given to the formula, so the entropy is therefore equal to negative 0.757 kilojoules per degree Kelvin. Now this problem involves work. The work is done in the system. Since the W here, the computed W previously, is less than 0, and heat is transferred to the substance. Since the value of Q is greater than 0, and since delta U is positive, then there is an increase in internal energy, and there is an entropy involved here. Now, this is the PV and the TS planes for this problem. So this one is the same with the first problem that solved previously. Now for problem 46, a gas composition is not known, has 42.2 kilojoules of paddle work, input at constant volume of 566. Initially, P sub 1 is equal to 138 kilopascals, and P sub 1 is equal to 26.7 degrees Celsius. Finally, T sub 2 is equal to 82.2 degrees Celsius. What are delta U and Q if K is equal to 1.21? So the given here, remember the given, so for the T sub 1, we have to convert it into degree Kelvin, as well as the T sub 2, so we just added it by 273. And then for the CV, since the specific gas constant is not stated in the problem, then we're going to use the universal gas constant. And the value of universal gas constant is 0.377 kilojoules per kilogram degree Kelvin. So for formula operation, CV is therefore equal to 39.6 kilojoules per kilogram degree Kelvin. Now, in order to solve for the mass, we're going to use the Avogadro's law. The formula for the Avogadro's law, which is equal to P1 V1 equal to mass times the R times T sub 1. So transforming this equation, we have the value of mass equal to P1 V1 divided by R times T sub 1. So substituting all the given to the equation, mass is therefore equal to 31.32 kilogram. Now for the delta U, you have the formula for delta U here. Delta U, mass times the specific heat times delta T. Now substituting all the given to the equation, delta U is equal to 68.9 kilojoules. And for the Q, since the formula for Q is equal to delta U plus the W or the work input. So substituting all the given to the equation, del Q is therefore equal to 26.7 kilojoules. Now this is the PV and the TS planes for this problem. So the work in this problem, work is done by the substance since the W is greater than 0, and since the delta U here is positive, then there is an increase in the internal energy, and heat is transferred to the system since the value of Q is greater than 0. Next, for a constant pressure system whose mass is 80 pounds, 1 HP per minute is required to raise its temperature of 1 degree Fahrenheit. Determine the specific heat for the system. BTU per pound degree Fahrenheit. So the given, so this problem is in isobaric one. So the given, for the following given, and in order to solve for the CP, we're going to use the formula for the equation Q. We have there Q, which is equal to the mass times the specific heat and delta T. Oh no, I mean this one. Since the pressure is constant now for delta Q, we have the formula mass times Cp times the delta T. Now, to find for Cp, since we're just going to substitute all the given to the equation, and then Cp therefore is equal to 0.53 BTU per pound degree Fahrenheit. So in this problem, heat is transferred to the substance since Q is greater than 0.